Good morning to student. So hello dear student. Good morning to all of you, and a special good morning to JNV Dawar. So we are here with the next session on question discussion on KTG and thermodynamics part 3. Okay. So firstly, make sure the screen is visible to you and I'm audible to you. If it is so, please write this thing in the chat box, or you can give me a thumbs up also. And please check that if we are live on YouTube or not. Okay. And please let me know as soon as possible. Okay, then we will start our lecture. Okay. So is the screen is visible to you? Okay. So here we are with the question discussion on KTG and thermodynamics part 3. Okay. So as usual, we will take questions, get up the solution, and try to understand the concept behind them. Okay. All of them will be the PYQs, most of them the PYQs, and there will be the conceptual question that will help you out to understand the concept, and that has the probability to become in the examination that you are aiming for. Okay, so let's just discuss question number one. Now, in this question, a container of volume 200 centimeter cube contains zero point 0.2 mole of hydrogen gas and zero point 0.3 mole of argon gas. Now the pressure of the system at temperature 200 Kelvin will be. Now in this question, container volume is given to you. It doesn't say that this volume specifically belong to hydrogen or argon. So we can assume that this volume is the volume of this mixture. Okay. Good morning, student of JNU Jamnagar. How are you? So in this question, the volume which is given to you is not specifically belong to hydrogen or not specifically belong to argon. So we can say that this volume is nothing but the volume of mixture here. Okay. Same for the pressure that you are going to calculate, and it is also given in the question that pressure of system has been asked. Okay. So the question itself assuming that you will try to find out the pressure of mixture, and the temperature is given to you 200 Kelvin, that is also belong to the mixture. Okay. So you can apply the ideal gas equation here, that P of mixture is equals to, just a second, V of mixture is equals to mu of mixture, mu is the number of mole, R into temperature of mixture. Okay. So what we can do, we will put the value P mixture, we have to find out volume of mixture 200 centimeter cube it is given. So we have to convert it into meter cube. So it will become 10 raised to the power minus 6 meter cube. Mu of mixture is 0.2 plus zero point 0.3. This is the total number of mole of mixture. Now, R is given to you as 8.3, multiply by temperature of mixture is 200 Kelvin. Okay, so try to find out according to the unit given of R. So here R is given in joule, Kelvin and mole. So we would put the value of temperature in Kelvin. Okay. Now, so you are saying that option C is correct, huh? So let me see. So it will become 0.5 multiply 8.3 multiply by 200 divided by 200, 10 raised to the power minus 6. So this 200 and 200 will cancel out, and this will become 5 3 15, 5 8 is 40, and 40 plus 1 is 41. Okay, and it is 4.15, 10 raised to the power, because two decimal places we have here. Okay, so it will become 10 raised to the power 6. So 4.15, 10 raised to the power 6 Pascal. That is the correct option. Okay. Option D is correct. Okay, although this value is correct for you yourself, so you have made a mistake in this. So here it is 4.15, 10 raised to the power 6. I hope it is clear to you. Okay, so move on to the next question. So the temperature of a gas is minus 50 degrees Celsius. Okay, to what temperature the gas should be heated so that the RMS speed is increased by 3 times. Okay. So the initial temperature is given to you minus 50 degrees Celsius. Now we know that we have derived the formula for, or we have know the formula for VRMS, V average, and what I would say VMP, which is most probable speed. So we are going to use that same formula here. Okay, but not the exact one. We will try to compare, because here we know that the speed is increased with increase in temperature. So only the thing that we need is the relation of VRMS with temperature. So we know that VRMS, meanwhile you can also solve it. Okay, VRMS is equals to square root of 3 RT upon M, where M is the molar mass. Okay. Now from here you can say that VRMS is directly proportional to root T. Okay. So square root के proportional है temperature के VRMS. So very simple. So we can say that VRMS initial divided by VRMS final is equals to square root of T initial divided by T final. Simple analogy. Okay. So option A you are saying, na? We see, is it correct or not? And it's very good that you are solving the questions. So VRMS initial is, let's say V. We assume it is V. Now this value is increased by 3 times. Initially it was V and then it has increased to 3V. Okay, V to 3V. That what is the V final? It will be V plus 3V, which is equals to 4V. So what does student do here? They will put the 3V here and they will not get the answer. Okay. So do not make this mistake. I have told you again and again that read the question carefully. Okay. Question itself has an answer in itself. So the final speed that we have is 4V. This will become 4 times V. Initial temperature, we need to convert the temperature into absolute scale, which is Kelvin. So minus 50 degrees Celsius, to convert it into Celsius, we need to add 273 into it, divided by T. So this will become 223 divided by T is equals to 1 upon 60. Now if you multiply this, it will become, just a second, it will become 16 into 3568. 3568. But this is in Kelvin. So no option given in Kelvin says that. So we need to convert it into degree Celsius. So for converting the Kelvin into degree Celsius, we need to subtract 273. So minus 273, it will become 3295 degrees Celsius. So the same temperature is 3295 degrees Celsius. So very good, brilliant answer. You have got it correct. Very good. Keep it up. So this is the answer. So as you have already got the answer, I don't think that you have any kind of doubt in this. Now this one, try to solve this one. I'm giving you 1 minute, 2 minutes, let's say. I'm giving you 2 minutes to solve this. Let me know the answer. It is given in the question that RMS speed of oxygen molecule, and oxygen is diatomic gas, so keep in mind. So RMS speed of oxygen molecule in a vessel at particular temperature is 1 plus 5 by x raised to the power 1 by 2 into V, where V is the average speed of the molecule. Now the value of x will be. Okay. So try to solve it. So we know that VRMS is equals to square root of 3RT upon M, and V average is equals to 8RT by pi M. Okay, got it? So I will solving it. Meanwhile, you will solve it and let me know the answer. Okay. So it is given that the VRMS here is equals to 1 plus 5 by x raised to the power half into V average. This V is nothing but the V average. Okay, option C here you are saying? Option C. Okay. So let's see. So VRMS here is square root of 3 RT upon, let's say, this is M is equals to 1 plus 5 by x raised to the power half square root of 8 RT by pi. So if you square it on the both side, it will become 3 RT upon M 1 plus 5 by x raised to the power half, and we will square it, so it will become 1 plus 5 upon x into 8 RT upon pi m. So this RT upon m will cancel out. This expression will become 3 into 3 is equals to 1 plus 5 by x into 8 upon pi. Got it? Now, what we can do, we can take it in this side. This is in multiplication, so here it will come in divide. So it will become 3 by 8 by pi 1 plus 5 upon x. Now this pi will go upside, 3 into pi upon 8 1 plus 5 upon x. Okay, so if you solve it, this will become 3 into 22 by 7, that's value is given to you, divided by 8 1 plus 5 upon x. Now if you solve it further, the value of x that came out to be, I'm writing it directly here. So the value of x that you will ace here is 28. So you are absolutely correct. Congratulations to you. So you're absolutely correct. You got it correct. Very good. Now move on to the next question. Try to solve this question. Okay. A diatomic ideal gas is compressed adiabatically to 1 by 32 of its initial volume. Now, if the initial temperature of the gas is Ti and the final temperature is alpha Ti, now what is the value of alpha here? Okay. So very simple question. And the options are, option A is 4, option B is 8, option C is 2, and option D is none. Okay, so try to solve this. I'm giving you 1 minute to solve this question. Okay, we are showing option A. Okay, so let me see what is this. Now, this is the diatomic gas. Okay, and it is compressed adiabatically to 1 by 32 of its volume. Adiabatically, which means process is adiabatic. Okay, of its initial volume. Now the initial temperature of the gas is Ti and the final temperature is somehow alpha T. So we have to find out the value of alpha. So here directly it is given to you the relation between temperature and volume. You need to establish a relation between temperature and volume. Now we all know that for adiabatic process or adiabatic process, T1 by T2 is equals to V2 by V1 raised to the power gamma minus 1, or simply in general you can write T V raised to the power gamma minus 1 is equals to a constant. This is the another form of adiabatic process. Now initial temperature is given to you Ti, final temperature you are aiming for, let's say we have assumed it T, is equals to V2. Finally, it is compressed to 1 by 32 of its initial volume. So V2 will become 1 by 32 of its initial, which is V1, divided by V1, gamma minus 1. Now gamma for adiabatic process is 7 by 5. Okay. Now this you can cancel out. This will become 7 by 5 minus 1. So it will become 1 by 32, and 1 by 32 you can write 1 by 2 raised to the power 5. Multiply with this power, which is 2 by 5. Okay. So this 5 and 5 will cancel out. So what the answer that you have is 1 by 4. Now T is finally is become 4 times of Ti. Now in this question is given that final temperature is alpha Ti. T final is alpha Ti. If you compare it, you will got the value alpha is equals to. Okay. Now I will tell you, you got it correct. I will tell you one thing, that this question is not from JEE Main and not from NEET. So you can guess. This question is from JEE Advance. Okay, in 2011, the name of the exam is IIT JEE. So this question is IIT JEE 2011, integer type question. Okay, so very good, very brave. Keep it up if you are really solving this. Okay, now, and I trust you that you are really solving it. Okay, now this question, try to solve this one. An ideal gas has a molar heat capacity Cv at a constant volume. Now find the molar heat capacity as a function of volume if the process of the equation is given as T is equals to T naught e raised to the power alpha V. Now try to solve this one. Okay. Put it. This is the ideal gas and the molar heat capacity Cv at a constant volume is given to you. Now you have to find out the molar heat capacity as a function of volume if the process equation is given to you this. Now we need to move according to the first law of thermodynamics. So by first law of thermodynamics, just a second, I will let you know the answers in option so that it will be easy for you to guess the answer. Okay, just give me a second. So here I am writing the answer. Option A here is C is equals to Cv minus R upon alpha V. Option B is C is equals to Cv minus 2R upon alpha V. Option C is C is equals to Cv plus R upon alpha V. And option D is none. None of the above. Okay. Try to solve this. The the question that it will said that molar heat capacity, na, finally that we have to find out. This molar heat capacity is nothing but the molar heat capacity of constant volume. So we have to relate it as a function of constant. This is the molar heat capacity that we need to find out the molar heat capacity at constant pressure. Okay. So we need to relate this molar heat capacity at constant pressure to constant volume. So that is why in the option you can also see this is the relation developed between Cv and C. So C here is nothing but the molar heat capacity at constant pressure. Okay. So welcome student. How are you? Now, now we know that first law of thermodynamics is dq is equals to du plus w. Got it? Now we know that dq is nothing but the we can write it as dq we can write as ncv sorry ncp dt, because we know that at constant pressure the heat given to it, the heat given to an ideal gas or a system will going to change the internal energy of it and going to do some work. So that we can write it as ncp dt. And du we can write as it is simply ncv dt. So this du is nothing but if you take the constant volume process. So at constant volume process, the work done will be zero. So all the heat is going to convert the change the internal energy. So we can say that du is nothing but ncv dt. Now Cp ko I will assume C because in option it is given C. So I can write it as Nc dt is equals to Ncv dt plus this P into dV. This is the work done, P into dV. Now, for n is equals to 1, I have assumed that number of mole is, so it is C into dt is equals to Cv dt plus P into dV. Now we need to find out C, so we will divide this whole expression by dt. So it will become Cv plus P dV upon dt. Okay, got it? Okay. Now, now in the expression, if you will see carefully, in the expression there is no pressure term. So we need to replace this one with another things. So from ideal gas equation, from ideal gas equation, we can say that PV is equals to nRT. Okay. So N here we have taken 1. So P we can write as RT upon V. So put it in this, let's say is the equation 1. So we need to put it in 1. So what will it become? C is equals to CV plus P dV by dt. This is we have P dV by dt. Now the value of P we have to put RT upon V. C is equals to CV RT upon V. This is dV by dt. Okay. Now the process equation that is given to us is T is equals to T naught e raised to the power alpha V. Okay. So what we will do, we will use it. Now this is equation number 2. Process is given to you as T is equals to T naught e raised to the power alpha into V. Now take log on both sides. This is the very conceptual question, okay, and very important. Take log on both sides. So it will become log on E base. Okay, we are taking log on E base. Or you can say we are taking ln simply. Taking ln on both sides. So it will become ln t is equals to ln t naught e raised to the power alpha v. So you all know the property of logarithm. The multiplication will be lead to as addition. So we can write it as ln t naught plus ln e raised to the power alpha v. So it is ln t naught plus power will come in front of the logarithmic. So it will become alpha v ln e and base is also e here. So this is the property of log, that log base a is equals to 1. This will become 1. So that is why we have written it as alpha v. And this is ln t. Now in the final expression we have dv and dt. So we need to differentiate this term so that we can get dt and dv also. So if you differentiate this, this will become 1 by t is equals to, this is the constant. So this differentiation with respect to temperature will become 0. This will come out to be 0. And finally, alpha v you can write as alpha into dv by dt. Okay. So from here you can put the value of dv by dt as 1 upon alpha t. So dv by dt you can write here as 1 upon alpha t. Now put it in 2. Okay. So what do you have? You will have C is equals to Cv plus RT upon V into, what is the value of dv by dt? It is 1 upon alpha t. T and t will cancel out. So it will become C is equals to Cv plus R upon alpha V. So this is the molar heat capacity. At constant pressure it is, but you can say it in general, the molar heat capacity in terms of molar heat capacity is a function of volume. So this is the molar heat capacity. Heat capacity as a function of volume. Okay. Now which one is correct? So option C is correct. C is equals to Cv plus R upon alpha V. Now, anyone, any kind of doubt in this question? You can ask. Anyone? Student from JNV Bhavnagar and JNV Ramnagar. Any kind of doubt in this? You can ask anytime, okay? Now, this one. Try to solve this one. The same is the same question, same concept we are going to use here, okay? So find the relation between volume and temperature. Now you have to find the volume relation between volume and temperature. In the previous one, if you will see, the relation between volume and temperature is given to you, and you need to find out the relation between Cp and Cv. Now, in the next question, what is the modification of this question will be the relation between Cp and Cv is given to you, and you need to find out the relation between volume and temperature. So same, but in a reverse manner, you have to do the things. Okay. Now try to solve this. Okay. So before I solve this question, I will let you know the very important formula or the concept of mixture, which is not relatable to this question, but you can expect the question from this topic. So try to note each and every formula that I will write here. It will ultimately going to help you in various ways. Okay, got it? So I will write here is some important, or I will write some very important formula. Very important formula. Matlab, you can expect a direct question from this topic, but if you are not clear with this formula, then you are not going to solve, or you are not able to solve that questions. Okay, so first of all, just give me a second. Mm, okay, so the very first formula that we have here is equivalent. Try to note each and every formula, okay? Equivalent molar mass. M equivalent. If a mixture of two gases is given to you, then what is the equivalent molar mass of that mixture? It is given by N1M1 plus N2M2 divided by N1 plus N2. I will write here that N1 is the number of mole of one gas, and N2 here is the number of mole of another gas. Same here, the M1 is molar mass of gas 1, and M2 here is the molar mass of gas 2. Okay. Now, uh, equivalent mole, so you can just directly add that mole, n plus n1 plus n2. Now, internal energy of the system, internal energy of mixture is given to u1 plus u2 plus u3. So, so whatever be the values, you can just directly add to them. Okay. Now, if I talk about the CV, molar heat capacity, this is important. Molar heat capacity at constant volume. So this is nothing but CV. So CV of mixture, mixture of two gases. CV of mixture is what? N1 CV1 plus N2 CV2 divided by N1 plus N2. Okay. In similar way, you can write CP of mixture, CP, molar heat capacity at constant volume, sorry, constant pressure. So it is N1 CP1 plus N2 CP2 divided by N1 plus N2. Okay. Another formula of CV you can write here in terms of degree of freedom. Okay. If let's say you do not have any idea, but the degree of freedom is given to you. So what you can apply? It is so CV you can write CV of mixture is F of mixture. F is the degree of freedom of mixture into R divided by 2. Okay. F of mixture into R divided by 2. So this is another formula. Similar way में you can write CP. So CP is, now we can also use the relation that CP is equals to R plus CV. Hmm? So CV is F mixture plus R by 2. So it will be 1 plus F of mixture by 2 into R. So this you can remember. Now how to find F of mixture? So it will be F of mixture is N1 F1 plus N2 F2 divided by N1 plus N2. This is another formula. And the last but not the least, the important formula that I am going to write here is gamma, for gamma. Okay. So one of the formula is gamma of mixture is Cp of mixture divided by Cv of mixture. Okay. Now, but in general term, what you can say that N1 plus N2, the relation is gamma of mixture minus 1 is equals to N1 upon gamma 1 minus 1 plus N2 upon gamma 2 minus. Okay. So this you can remember for gamma mixture. Now, one of the gamma mixture formula is also that it is Cp of mixture divided by Cv of mixture. So this you can also remember, but in general it is given by this. So you can either take the screenshot or you can note it down. And when you note it down, you please let me know that you have noted down, okay? So that we will move on to the question that we have in our hand. So have you noted down? Any yes and no? Okay, you can expect a direct question from this topic, okay? In NEET and in JEE both. Okay, got it. Now, focus on this question. This is C is equals to CV plus alpha T is given to you. Now, we know that according to first law of thermodynamics, according to first law of thermodynamics, what we will say that dq is equals to, this is the differential form of first law of thermodynamics. dq is equals to du plus w. We have already did this calculation in this. So dq is equals to du plus w, nc dt, cv dt, p dv. Okay. For n is equals to 1, we have developed this relation that c is equals to cv plus p into dv by dt. Now, if you put the value of p, finally I'm writing it here. So this will come out to be c is equals to cv plus p dv upon dt. Now c is equals to cv. Now you need to put the value of p, which is rt upon v, dv by dt. Got it? Now this is the relation number 1 that you got. Okay. Now if you compare it with given values, which is c is equals to cv plus alpha into t. Okay. So what do you have? This is equation number 2. Now compare. Comparing equation 1 and, so what do you have? You have alpha t is equals to rt upon v into dv upon dt, because cv and cv got cancelled out. Okay, so this will only left thing, which is rt upon v dv by dt is equals to alpha t. Now t and t you can cancel out, so you will have alpha v is equals to dv by dt. Okay, so what we will do, we will take dt here, alpha dt here, and dv by v, we will take this on denominator. So dv by v is equals to alpha dt. Now if you integrate this, so what will have? 1 upon v का integration we have ln v, and this is alpha t plus, somehow we have here we will assume an arbitrary constant which is c, or instead of c you can whatever you can assume, because c is given to you as a the molar heat capacity, so we will assume that it is ln k. Okay, simple. Now this ln k here is the arbitrary constant, because this definition, this integration is not definite. So to make it definite, we need to add some constant. So that is the arbitrary constant. Arbitrary constant. Okay. Now what we will do, ln v is equals to, we can write this alpha t as ln e e raised to the power alpha t. Okay, plus ln k. Now we are able to write this because we know that property of logarithmic, that log base a raised to the power on base a raised to the power b, you can write it as b. Okay, because b will come out in the front of log and it will become log a base a. So this will become 1. So that is why you can write it here as it is. So same way we have do it. Okay, because all the bases are e, so we have take the ln here. Now ln capital V, ln e raised to the power alpha t into v. If you remove this, what you will have? You will have v into e raised to the power minus alpha t. We will take e here is equals to k. So this is the final relation that we have developed between volume and temperature. So that is the question has been given, that a question has been asked, that the find the relation between volume and temperature of the gas. Okay, got it? So I hope you got this. Any kind of doubt in this? I don't think so if you have any kind of doubt. Okay. So I hope we would terminate our session here because it's 10:55 now. Yeah. So just give me a second. So this question you can note it down. Okay. Or what we will solve it right now. Try to solve it or not. Yeah, this is your HW. Okay, got it. Okay, this is your HW. Okay. So try to solve this question, that 5.6 liter of helium gas at STP is adiabatically compressed. Okay, 2.7 liter. Now taking the initial temperature to be T1, now what is the work done in the processes? Okay, so I will let you know the answer. What is the answer of this question? Just give me a second. Yeah, thank you so much. Uh, just give me a second. I will let you know the answer to this question so that it would be easy for you to solve that. Okay. So option A is 9 by 8 RT1. Option B is 2 by 3 RT1. Option C is 15 by 8 RT1. And option D is 9 by 2 RT. Okay. So if you are able to find, because this is the compressed, so the work done is on the system. So you need to take, if work is done by the system, you will take positive. If work is done on the system, you will take as negative. So work done will be came out to be negative. So you have to take the simply mode of that work done because all the values here are in positive values. Got it? So thank you so much for being attentive. Any kind of doubt if you have, you can ask right now. Otherwise, the lecture is being over. Thank you so much for being attentive. Take care of yourself.